Now, in the case of what you're looking at in question 1, I believe that every critical value of x in either of these graphs will correspond to a max-min. By the way, it's occurred to me that there can be another type of critical value of x that is not a max-min. We said yesterday that you can have a critical value of x that's not a max-min if you had a hole, or if you had, it's really an inflection point where the slope of the graph is infinite at that point. And if the slope of the graph is infinite, then the derivative is undefined. But you can also have another inflection point that's so severe that at this particular value of x, it's critical because the derivative will be equal to 0 there. The slope of the tangent at this point will be 0. But because the function increases up to that point, and then it immediately increases after that point, since it's not changing direction, it's not a max or a min. Just to finish this off, remember, all critical points are not necessarily max-min, but every max-min must be a critical point. If you have a closed interval like any of these in number 4, there's no need to construct the first derivative table. You're simply figuring out what f of the critical value of x is for every single critical value of x. And whichever function value is the greatest, that will be the absolute maximum. Whichever is the least, that will be the absolute minimum. If it's an open function, or a function over an open interval like those in number 3, remembering that I don't want you doing any with absolute value. If it's an open interval, then you need a first derivative chart. The lesson today is not a lengthy lesson because, as I said, yesterday kind of was the pinnacle of what we're doing, and then we're going to ease off a bit today and pull it all together. And I hope it makes sense. It should, after spending all the time we have on these. So we have some time here to go over questions. Does anybody have any specific questions from that list that you would like me to go over? Go ahead, JV. 2H. Okay. Say that again. A? 2A. So we have 3x minus 1 where x is greater than negative 1. Boy, this is a weird one. This is really going to test our patience in understanding critical points. And the reason why is it's not saying x is greater than or equal to negative 1. It's saying x is greater than negative 1. And this function in and of itself, let me rewrite it, is a pretty simple function. It's y equals 3x minus 1, which is a straight line, but we have this interval. I don't know whether we can really call it a closed interval, but it's not really an open interval. It starts at a particular point, which is a bit of a lie, but it continues to infinity. So the interval here is from negative 1, let me just double check that, from negative 1 up to infinity. Of course, you can't be at negative 1 because of the statement in the question, and you can never reach infinity because you would go crazy trying to get there. This is a really interesting question because it's just a linear function, right? And you can probably analyze this without talking about calculus in terms of derivatives, but I'm going to go ahead and find the derivative. dy dx is equal to 3, which is no surprise here, JV, because the function y equals 3x minus 1 is a straight line with a y-intercept of negative 1 and a slope of 3. So if I said to you, look at this derivative and tell me what the critical values of x are, I think the reasonable response from most people would be to say, well, there aren't any. Because 3, which is the derivative, can never be 0. There's not even a variable in there. And 3, which is the derivative, is never undefined because 3 is 3. But 3 is defined as 3. It is a definite value. But there is a critical value of x here, and this is a strange critical value of x. The critical value of x is -1, and I'd be willing to go out on a limb here and say that the answer in the back says there is a minimum value of -4. I'm willing to bet. If there isn't, that will make me very happy, because if there isn't, it's correct. The answer in the back is correct. What does it say for the answer? Excellent. So the answer in the back is correct. So let me explain to you why there are no max or mins. And this is really going to stretch the idea in your head of what's going on here. What we would say is that x equals -1 is critical because, what's the best way to put it? I guess because that's where the function starts. Does anybody want to volunteer why that's not a true statement, that the function doesn't start at -1? Liam? Right, the function doesn't exist at -1. It exists greater than -1. So if we were to graph this, and by the way, with this question, that's what it does ask you to do. And I should have said yesterday, for this question, there's nothing wrong with graphing it on your calculator, but we could graph it without a calculator. I'm simply going to look at what the graph of 3x minus 1 looks like. It is a graph with a slope of 3. And a y-intercept of -1. So this y-intercept is -1 and it has a slope of 3. But if this function is only defined when x is greater than -1, now it's unfortunate we have two -1s floating around on the board, but the -1 that refers to x is referring to this point over here. Because the graph is only defined from negative or to the right of -1, that means down here, I'm just going to stretch this out a bit more. That means down here, where this point is, that this point isn't. Where x equals -1 JV, there is no point. So what the graph actually looks like is this. And I just want to fix that a little bit more. So from a standpoint of critical points, everybody, is it true that the derivative is not defined there? Well, yes, it is, because the function isn't defined there. But that's about as meaningful as saying that saying x critical equals -1 is about as meaningful as saying x critical is also -2, because the derivative isn't defined at -2. It's not. But if the derivative isn't defined because the function isn't defined, we can go with one of two outlooks here. One is to say, yes, that is a critical value of x. But it will never be a meaningful critical value of x that gives a max or a min. Now comes the part that's going to twist your head around a little bit. The reason there is no minimum value, this y-coordinate here, JV, is -4. The y-coordinate of the hole in that graph is -4. The reason there's no minimum value is because no matter what value you assign to the lowest point that is defined on the function, you can go lower. But if you say, well, the minimum value can't be -4 because the function doesn't exist, but then you go, well, I know, it's -3.999. Well, that's not the minimum value. No matter how close you get to -4 on the graph, you can always get closer. So that's why I'm pleased that the textbook says there's no max or min. And clearly there's no max because it goes up forever. Go ahead, Evan.
Just a random thought. It's probably not right based on what you said, but what if we define the minimum as a limit?
The problem with that, we can't weasel our way out of it. It's still going to be the case that there's no minimum, because what you're then saying is, what Evan is suggesting is, let's say that the minimum value is the limit as x approaches -1. It would have to be from the right of the function. And the fact of the matter is that limit is equal to -4. But because the point doesn't exist, that -4 cannot be a minimum value. Which means this initial statement that you've come up with is not logically valid. We're coming to a conclusion based on an assumption that you had. We come to a conclusion that's impossible, that there is a minimum when we know there isn't. It's a mathematical trick that doesn't work. Yeah, it's kind of like, I don't know if you remember, but in Physics 30 last semester we did some problems where we didn't know if a mirror was concave or convex, but we would pick one, and then if we got an impossible answer, we would say, well, it isn't the one we picked. That kind of logic is what's going on over here. Is this a valid conclusion or a valid assumption? Well, it leads to an invalid conclusion, so the assumption doesn't work, unfortunately. It's a great idea, but it just is not logically sound. Other questions? Go ahead, Arden. For E? So we have x to the 4 minus 2x squared plus 16, and it is a closed interval. And what that means, Arden, is we're simply going to make a list of all of the critical values of x, and we are going to find out what the y coordinates are at each of those critical values of x, because on a closed interval there must be an absolute maximum and an absolute minimum. The critical values of x have to include where the function starts and where the function finishes. And again, just to go through that briefly, I'm not suggesting that what I'm about to draw is what this graph looks like. But if the graph starts at -3, let's just say this is -3 here, and ends at +2, and it's probably worth noting that this function is polynomial, which means it's continuous everywhere. The function will be continuous everywhere from whatever its value of y is here to whatever its value of y is here. Whether they're positive or negative, it doesn't matter. And the only way to draw a continuous function between those 2 points, and again, I'm not suggesting this is what it looks like, but is to draw a continuous line without lifting your finger. No matter how you draw that, you are going to get an absolute maximum and absolute minimum. We don't need a chart to do that, though. We don't need a first derivative chart. So, oops, going the wrong way here. I'm going to find the derivative of this function f prime of x is equal to 4x cubed minus 4x. I'm going to factor this, Arden, so that I can look by inspection and see what the critical values of x are. So I factored 4x out of both terms because that's a common factor, leaving me with x squared minus 1. And x squared minus 1 factors into x plus 1, x minus 1. So I also have a 0 that's critical, a critical value of x of 0 because of the 4x, and then +1 and -1. And now all I have to do is put these numbers into the function. But I would recommend here not actually, going through the grunt work of entering the number raised to the 4 minus 4 times the number, etc., or whatever it was, minus 2x squared. So I'm going to put this in for y. There we go. Y equals x to the 4. That's x times x times x times x minus 2x squared plus 16. You can feel free to enter it however you like. This is just my way of making sure I've entered it correctly. I'm going to go to my table. After setting my table up to be on ask mode for the independent, which is x. By the way, the next line in this does nothing. You would think that if you put ask for the dependent, you could enter in a value of y and it would calculate x. It doesn't. I don't know what it does. So I go in here and now I'm just going to enter all of those numbers. Negative 3, 2, 0, 1, and negative 1. The largest value of y I get is 79, so the absolute maximum of the function is 79. And that occurs when x is negative 3. In other words, at the beginning of the function. The lowest point we get is 15. So the absolute minimum is 15, which happens to occur in 2 places. If I were to look at the graph here, I'm going to set my window settings to go from here, Arden, to go from negative 3 to 2 because that's the domain. And I'm going to set my window settings vertically to go from a little bit less than 15 up to a little bit more than 79. So negative 3 to 2. And let's go 13 to 81. This function has some symmetry to it. It comes down from this maximum point where it starts, comes down, there is a minimum here, it rises up, there is a local maximum, then there is a minimum again, and then it rises. So all of these points that I'm indicating are points that are critical. This one here clearly is the absolute max. These two here clearly are the absolute min. This point is a local min, this point is a local max. The point on the left is critical because the derivative is not defined. The point on the right is critical because the derivative is not defined. The 3 points in between are all critical because the derivative is 0. Does that help? Yeah.
I'm just wondering, why doesn't the graph go to infinity so that there would be no max?
It doesn't go to infinity because the equation, when you have an equation of a function, that tells you what the graph looks like, right? The equation of this function also includes, as well as the rule for calculating y, it includes the rule for the values of x that you're allowed to use. So because we say, comma, negative 3 is less than or equal to x, which is less than or equal to 2, we're saying that's part of the rule of the function. You can only use those values of x. Without that, you're right. There would be no absolute maximum because it would go up forever. Any other questions? Number 5. Show that this function does not have any max-mins. None. So we have, for number 5, y is equal to x to the 21 plus x to the 11 plus 13x. And this is going to be very close to what we talked about yesterday with the question that I believe Mackay asked about. That the derivative turned into a degree 4, which we thought of as quadratic. And let's go ahead and find the derivative here. And by the way, Marcel, this function is defined over all real values of x. So it doesn't start in a place and end in a place, everybody, which means the critical values of x will only be found by looking at the derivative directly. This will be 21 x to the 20 plus 11 x to the 10 plus 13. And you learn about these types of, what do I want to call them? I guess I'll just call them polynomials. You learn about these polynomial expressions and factoring them in Math 20-1. There's this little tiny lesson where you talk about the fact that this exponent is even. This exponent is half of that even exponent, and the power on x here is nothing. And this makes it quadratic because, everybody, and I didn't explain it to you this way yesterday, I'll do it now. This can be written as dy dx equals 21 x to the 10 squared plus 11 x to the 10 plus 13. It's quadratic. It's a times a thing squared plus b times a thing plus c. In other words, and I'm just doing this hopefully in such a way that will allow you to see why it's quadratic. If it's factorable, and it's not, okay, I don't believe this is factorable. If it's factorable, you would have a number of x to the 10s plus some other number times a number of x to the 10s plus some other number. Now, it's not factorable, I don't think. We're about to find out in a minute, but that's not my point. If you tried to factor this, if you could, as a grade 10 student, wrap your head around the x to the 10s, you would probably put something like 3 here and 7 there. And I want you to just look at that and see how that will give you 21 times x to the 10 squared. You see how that would work, Arden? I get 3 times 7 is 21. And then I get x to the 10 times x to the 10. 5 times 5 is 5 squared. 2 times 2 is 2 squared. X to the 10 times x to the 10 is x to the 10 squared. I mean, it's x to the 20, but it's x to the 10 squared. And you might put numbers like this here, 13 and 1. But here's my point, which is why this thing that I'm pointing at is quadratic. Your inner and outer will be a number of x to the 10s. So when you add them together to get your middle term, you will get a number of x to the 10s. So this is why if the exponent on x is even in the first term, the exponent on x is half of that even exponent in the second term, and there is no x in the third term, it's quadratic. So after this big discussion about factoring this, is it factorable? Well, you've been given the tool, and I don't know if anybody at Nicole, Demi, and Zach have ever showed this to you in any of your previous classes, but the tool that we talk about here and is very useful is b squared minus 4ac. If this is a perfect square, then a quadratic is factorable. So if I calculate b squared minus 4ac here, and I'm just looking up here, I have 21, I have 11 squared minus 4 times 21 times 13. And I'm willing to bet that you're going to get a negative number here. And you can work out what the number is, but you get a negative number. So if b squared, I don't know what it is, it doesn't matter. If b squared minus 4ac is a perfect square, factorable. If it's not a perfect square, it's not factorable. But because this is negative, not only is this not factorable, there is no value of x in the universe that will make that 0. So who had asked about this? Arden. What that means is that that derivative, and I can get rid of all this other stuff now. What that means is that that derivative has no critical values of x, none. What does that mean? It means since the derivative is a polynomial and is defined everywhere, that derivative is either positive everywhere or negative everywhere. It never changes signs. And we don't need a chart to do this. I suppose you could say, let's look in our first derivative chart at this interval, and across the top put this derivative. But, you know, we're constructing a chart with an entire interval and the entire derivative. Why don't we just put a number in here for x? And I hope you see that no matter what number you put in for x, you are going to get a positive number. You can put 0, you can put 1, you can put a million, you can put -5. Because those exponents on the x's are even, you're going to get positive numbers. So if the derivative is positive everywhere and the function exists everywhere, then the function is rising everywhere. So whatever wobbling might be occurring, the function starts down here someplace in quadrant 3, wobbles around, but no matter what happens is it's always going up, always, because the derivative is always positive. So we've shown that that's the case, but let me show you the function now. This was x to, well, it's just going to be a line. It's going to be a line so steep because it's x to the 21. I will try to scale it so we can see it a bit more. I'll do my best. I mean, we're not even going to see anything. I don't think. What is it? Where am I looking here? Oh, plus 13x. The fact that there's an x in each term means that the function has a factor of x, which means it goes through the origin. But because it's x to the 21, it's going to be such a steep polynomial function through the origin, I don't think we'll see it. I'm going to go zoom standard, which is just a ridiculous notion, but I don't think we're going to see anything. My calculator's still grinding away because it's x to the 21. It's calculating a whole bunch of, oh, we can, look at that. I thought it would be even steeper. So I'm going to take a guess here. Well, not really a guess. Don't worry about my thought process there. I think it's going to come up again. Yeah. I don't know what it's doing in there, but whatever it's doing in there, in that flat portion, it's not going up and then down. It might just be going up slowly, 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 slowly to the origin and then continuing to go up. We would need to look at the second derivative to decide what's happening. Which, yeah, I see people go, what? The second derivative is going to tell us more information about the graph. Anyway, is that okay, Arden? Okay. Any other questions before we move on here? Go ahead. 4G. So we have x squared plus 16 over x. And again, what we want to do here, since it's a closed interval, is we want to make a table showing critical values of x that will allow us to find the values of y at those critical values of x. And that table has to include 1 and 4 because that's where the function starts and where the function finishes. When I differentiate this, I am going to first of all rewrite it as y equals x squared plus 16x to the negative 1, just to make it into a sensible form where I can use the power rule. I don't really like to work left to right, but I will in this case. dy dx is then going to be 2x minus 16x to the negative 2. Should be okay with that. We want to factor it in order to, again, you want to factor derivatives so you can see the critical numbers. That's why we're always factoring. And if I factor that, boy, I'm really working in a non-standard way here. I'm going to write the answer up here. dy dx is going to be found by factoring out the 2x and being left with 1. Pardon me. We're going to factor out 2x to the negative 2. We can factor out a 2 because there's a 2 in the 2 and a 2 in the 16. And we factor out the lowest exponent, which is x to the negative 2, giving us x cubed minus 8. Are you okay with that, JV? Okay, so what is the derivative? I'm all over the place here. This isn't very organized. But the derivative is 2 times x cubed minus 8 over x squared. That's the derivative. So that x to the negative 2, since it has a negative exponent, I toss it on the bottom. The 2 that I factored out is not part of that thing that's to a negative exponent. The 2 doesn't go to the bottom. The 2 stays on the top. Not that it matters. Yeah.
Would you want it further factored by a difference of cubes, or does it matter?
I'm going to address that in a second, and I'll tell you why the answer is no in my mind. I have a critical value of x here of 0, and I have a critical value of 2, and I'm not even looking at factoring x cubed minus 8 to determine that. What I'm doing is I'm saying if x cubed minus 8 equals 0, then x cubed has to equal 8, and I haven't broken any mathematical laws here. I'm not, there's nothing magical or mysterious about this. I'm just rearranging for x. So x equals the cube root of 8, which is 2. Okay? So let's talk about what Liam's asking. Should we factor it as a difference of cubes? I don't know if you recall. Well, let me get it factored first. Correct? So remember, we are interested in where this is equal to 0. And I hope you can see where the 2 pops out of that. But I don't know if you remember me saying this thing in a difference or sum of cubes is always a dead end. I don't know that I've used that term before, but it's neither factorable nor zeroable, if that's a word. You can never make that other factor 0, and you can never factor it. So that's why it's an unnecessary step here. In the end, the only time you want to use a difference or a sum of cubes is when limits are involved, and it will simplify things. So now, JV, you had asked about this. We're going to load those 4 numbers, those 4 critical values of x, into the function and see what we get. So you need to take x squared plus 16 over x when x is 1. And I'm going to quickly just do this. You can use your calculator if you like. I believe you get 17. 4 squared plus 16 over 4 will give you 20, I believe. 0 squared plus 16 over 0. You can't divide by 0. 0 is non-permissible, which is why it's a critical value of x. The derivative is not defined there. But it's not a definable value for y. When I put in 2 squared plus 16 over 2 is 4 plus 8 is, I believe, 10. How did I do on my calculations there? I think they're fine. So anyway, assuming those are the correct numbers, and I believe they are, the maximum, the absolute maximum value of the function is 20, and it occurs at the critical value of x of 4. And the absolute minimum of the value of the function, the absolute minimum of the function is 10, which occurs at a critical value of x of 2. Is that okay?
So just for like that whole difference of cubes thing, should we like never do the difference of cubes while we're doing this kind of work?
Well, no. The question is, should we just ignore differences in sums of cubes when you're doing this kind of work? And the answer is no, because this thing that I have in green is the simplified version of the derivative, okay? If you do factor that x cubed minus 8 as a difference of cubes, it's not going to get any simpler. Okay? This would be like, and I believe there was a question yesterday, and now we're just talking about math. Okay? There was a question yesterday that had somewhere in it x squared minus 9 maybe to the third. I don't recall. And I made a big deal out of saying, look, we know that x squared minus 9 is x plus 3, x minus 3. Will writing it that way make any difference? And the answer is no. But what if we did a derivative, JV, that involved, I'm going to do this, okay? That involved that, but along the top, you had a factor of x plus 3 quantity squared. Do you see how factoring the bottom would lead to a simplified version of the derivative? Okay, because x minus 3 is a factor of x squared minus 9. When we look at this, and it isn't the case, but what if you had the following? What if you had this as an additional factor in the bottom? Then simplifying the derivative, that job is not done yet, because you can factor that x cubed minus 8 to end up with that x squared plus 2x plus 4. And that just triggers something in my head. I believe I may have factored that difference of cubes incorrectly. I did. That shouldn't be plus 4x. That should be plus 2x. Anyway, I hate to answer your question like that, because my answer basically is, you know what? It depends. And that's the level of math that we're dealing with here. You always want to have a motivation for doing something. And if you view this math as just blindly walking down the alley doing the same thing every time, you might have difficulties. We are going to move on now. Even though it's a relatively short lesson, we are down to half the time remaining in class. So we're going to open up our books to the first derivative test, which I believe is on page 18. And really, everybody, you know what? There's nothing. There's absolutely zero that's new here. We're just kind of putting it all together now. We're going to use what's called the first derivative test to determine maxima and minima. In the lesson before yesterday, we learned how to determine where functions are increasing and where functions are decreasing. In yesterday's lesson, we learned how to find critical values of x and to explore the concept of local versus absolute max-mins. Well, we put these together to identify max-mins. So in your notes it says, assume that a function is continuous at a particular place, some value of x. The function exists before that value of x. The function exists after that value of x. And it exists everywhere before and after and at that point. If the first derivative changes from positive to negative as you pass through that point, then that point must be a maximum. I mean, think about it for a second. I can construct a graph here. If I have the following graph, We'll just make it simple and have something like that. And there is some value of x here. I'm calling it c. In this region here, the first derivative is positive because the graph is rising. And it's rising everywhere up to, but not including at c. And in this region over here, the first derivative, and I say first derivative because we're going to be going to a second derivative here in a couple days, maybe even tomorrow. The first derivative here is negative because the graph is dropping. The slope is negative. Well, that must mean right here, there must be a maximum. There's only one way you can go from rising in value to falling in value continuously, and that's to pass through a maximum. Similarly, if the first derivative changes from a negative to a positive, then that must be a minimum. So I'm still talking about c here, but I'm going to use a different letter. I'll just use a green c. The derivative everywhere between this point and this point, the derivative is negative. And then afterwards, the derivative is positive. How can you go from a negative derivative to a positive derivative continuously? By passing through the point where the derivative is 0 or undefined. We'll get to that in a second. Which means passing through a minimum. By the way, it could be like that. This is a negative first derivative. This is a positive first derivative. Whatever. This is a minimum, but the derivative doesn't exist there. So it could be 0 or, well, it's at a critical value of x. So as an illustration, if you were to make a chart, and this isn't in your notes and there's no need to write it down, but if I had a chart where I had on the side all of the different intervals that the function or derivative is defined by, broken into subdomains by looking at the critical values, and I complete this table, which we've done, and I discover that the first derivative is positive in one interval, and it continues to be positive afterwards, even though that was passing through a critical value of x. And then in the next interval, the derivative is negative, and then in the next it's positive, and then in the next it's negative. Then what does that tell me about the function? It tells me the function is increasing, and then continuing to increase, despite my suspicions that there might have been something funny going on there. There isn't. It just keeps going up. And then it's going down. And then it's going up. And then it's going down. What does that tell me? It tells me there's a maximum here. There's a minimum there. There's a maximum. A maximum there. Which I think you kind of knew. This is what we've been doing, but we're just putting it all together here. So we're going to do 2 quick examples. Find all maxima and minima for the following function. So the first thing I'm going to do is find dy dx by differentiating double checking. There's a lot of numbers there. Just want to make sure my thought is right. Looks okay. I want to factor this so that I can look at it and see what the critical values of x are. I can factor out 15x squared and be left with x squared minus 1. The x squared minus 1 is a difference of squares. So my critical values of x are -1, 0, and 1. And everybody, I've just chosen to put them in numerical order. This tells me that I need to construct a first derivative table that includes the interval from -infinity to -1, from -1 to 0, from 0 to 1, and from 1 to infinity. Across the top, I need to put all of my factors, 15x squared, x plus 1, x minus 1, so that I can figure out what the derivative is, so I can figure out what's happening to the function, so I can figure out where the max mins are. $15x squared is positive everywhere because 15 is a positive number, and whatever x is, when you square x, you're going to get positive. X plus 1 will go from being negative to positive as it passes the 0 of its factor. So the 0 of x plus 1 is negative 1. Before negative 1, this thing will be negative. After, it will be positive. The 0 of x minus 1 is 1, which means that this third factor will be negative up to that 0 and become positive after that 0 of 1. Multiplying these together, this is positive, and I'm not going to use a different color here, but I would recommend circling it in your notes, because then you know this is the culmination of those other three columns. Then it's negative, it's still negative, and then it's positive, which means the function is increasing in the first interval, then decreasing, it continues to decrease, and then it's increasing. Which means we are going to have a maximum here and a minimum here. Because the function goes from increasing to decreasing through a maximum, and it goes from decreasing to increasing through a minimum. So there's a max at, well, where is this? This point is where the interval negative infinity to negative 1 ends, and the interval negative 1 to 0 begins. So it's at negative 1, comma something, and we will have a minimum at positive 1, comma something. The value of x, that's this point where the derivative changes from negative to positive, the value of x there is 1. Now, how are we going to find the y coordinates? We're going to look at the function, not the derivative. You have to look at the function. So we're going to put negative 1 in for x. And I believe you get negative 2 for y. I could be wrong. I'm going to double check. I'm sorry, you get positive 2 for y. And when you put in positive 1 for x, you get negative 2 for y. Y is equal to 3x to the 5 minus 5x to the 3. I'm going to go zoom standard because don't forget I had those. I better double check that. It's okay. I'm going to go zoom standard because I had those wacky settings for that previous graph. I'm going to alter the window setting here just to show this to you. You're pretty familiar with how your calculator works. You can play around with this on your own as well. That's not what I wanted to do though. Let's try zoom in. I really am not a big fan of zooming in, but I think here we might be okay. Yeah. There's the maximum, there's the minimum. See how there's that twist, that inflection point in the middle? That's what's happening when the graph goes from decreasing to continuing to decrease. It's an inflection point. Any questions with that example? Evan?
It should make sense that we don't put the
That should be a tip-off. You'd be surprised, though, how often I will see that. Or maybe it's not how often I see that. Evan's saying you wouldn't put it back into the derivative because then you'd get 0. But I still get asked that question a lot, like, how do I find the y coordinate? Where do I put it? Yeah, you have to put it back into the function, definitely. And my point was, he's right, because if you do put it in, you get 0. That's probably a tip-off. That, oh, wait a minute, that's the derivative. That's not y. All right, let's try the second one, which is the last one. We want to differentiate this. Well, the first thing you want to do maybe is write this as 1 plus x squared to the negative 1 to avoid the quotient rule. I think the quotient rule is more trouble than it's worth here. Only because the numerator is a constant. So when I differentiate this, I have dy dx equals negative 1 times 1 plus x squared to the negative 2 times the derivative of what's inside, which is 2x. So I get dy dx equals negative 2x over 1 plus x squared squared. Critical value of x of 0, because the numerator is negative 2x, x equals 0 will make the numerator 0, which will make the derivative 0. So we have a critical value of x of 0. That's found by eyeballing the top of the derivative. Will eyeballing the bottom of this derivative give us any critical values of x? Well, no. Because then what you're doing is you're saying, well, if that's going to be 0, then 1 plus x squared will be 0, which means x squared will be negative 1, but you can't take the square root of a negative. There's only one critical value of x here, which means our derivative chart is going to be going from negative infinity to the 0, from the 0 to the infinity. Across the top, we can put negative 2x and 1 plus x squared squared. Just a brief addressing of something. Very often people will say, does it matter how I group the factors in the top of my derivative chart? So, I want to make sure you follow this. Because in the past, what I've maybe done is this. Now, don't erase it. It would look like that. And a number of years ago, I decided, why am I doing that? Why don't I just put negative 2x? That's easier. This is positive, and then it's negative. And that might require a little bit more thought because of the negative in the 2x. But the question that some people will ask is, does it matter how I group these? And my answer is no. Ultimately, this is your goal here, right? I just don't want you to get in the habit of writing the whole derivative there and having one column for it. I don't think that's mathematically healthy. This is positive. Why is it positive everywhere? Because it doesn't matter what x is, x squared is going to be a positive number. Now you might say, well, what if x is 0? X will not be 0 ever in this chart because 0 is critical. Even if x was 0, 1 plus 0 squared is a positive number. And this really rules the roost, doesn't it? I don't care what you have there. If it's raised to the 2, you're going to get positive. So the derivative is positive. The derivative is negative. We're multiplying or dividing these things. The function is going up, then going down. We have then a maximum here. So we have a max at 0, comma. Now I put 0 back into the original function, and I believe we get 1. I will tell you right now, I know what this graph looks like. I will show it to you, and then you can put it on your calculator if you like. What this graph will look like. It's a graph that we use in statistics all the time. looks something like this. There is a horizontal asymptote on the x-axis. It has a y-intercept of 1. How many of you can see, I just want to lead up to a further lesson, which will either be tomorrow or the day after. How many of you can see that there's something happening here? The graph changes its behavior there. And the graph changes its behavior here. And essentially, the shape of the graph before this point is this general type of shape. That if you had that shape, I mean, I know it's not quite like that because it only slopes up, but it has that upward curve to it. And over here, it has this upward curve to it. But in between, it has this downward curve to it. That's going to be what the second derivative reveals to us. The second derivative is going to tell us how the shape of the graph changes. It's called concavity. Anyway, you can feel free to graph that in your graphing calculator. These points, by the way, these inflection points, will be critical points of the second derivative. Some of you might see why, but most people won't just yet. That's it. We're just putting it together today. Questions 1 through 4 on 182 and then number 3 on 196. If you look at these just briefly as a class right now, all of these questions in number 1 are polynomials, which means any critical point is going to be where the derivative is 0 and it will be a max-min. Same with these. Starts to get trickier when you look at 3. And you and I know there's no way I expect you to do every single question, ever. But I would expect you to look at something like number 3 and go, well, that's weird. Maybe I should try something like that. Or maybe I should try something like A. 4, a few more wacky ones. This one is just some extra practice. Don't do any with absolute value. So you got lots of time here. I'm going to hand out your next assignment and hand back your last assignment. Okay.